Commutative property matrix addition, if we have a matrix, let's say 1, 2, and we add it to the matrix 3, 5, do you suppose we get the same answer as if we took the matrix 3, 5 and added it to the matrix, column matrix, whose entries are 1 and 2? You think they give us the same answer? I believe so. And it basically works because if we add these, 1 plus 3 goes right there, and 2 plus 5 goes right there. If we add these, 3 plus 1 goes right there, and 5 plus 2 goes right there. And because addition is a commutative property for the set of real numbers, we add 1 and 3, we get the same thing as if we add 3 and 1, we get 4. We get 4. And if we add 2 and 5, we get the same thing as if we add 5 and 2, we get 7. Works out nicely. So the fact that multiplication of matrices is commutative depends directly on the fact that addition is a commutative operation for real numbers. So works out. We could do something similar for the second one. If we wanted to illustrate it, we could say, 1, 2, take that and add it to whatever 3, 5 plus 7 negative 8, just trying to come up with numbers on the top of my head. You suppose we get the same thing as if we took the 1, 2 and the 3, 5 and added those together, and then took that resulting matrix and added it to 7, negative 8. Would that give us the same 2 by 1 matrix? Yeah, I believe it would. So for the same reason, because addition of real numbers is an associative operation. You can group them however you like to, and you add them to get the same answer. So matrix addition is commutative. Matrix addition is associative. Let's see, 3. What if we take 2 and multiply by 3, and then multiply by the matrix whose entries are 1, 2? You suppose we get the same answer if we take 2, and then hold on, multiply 3 by the matrix whose entries are 1, 2, and then wait, and then multiply by the 2. Basically, it's an associative type of property here, associative property of scalar multiplication, where one of the quantities is actually a matrix. But yes, it works just fine. I guess I need parentheses there. Multiply the 2 and 3 and get 6, and then multiply 6 by each entry, and we get what the matrix whose entries are 6, 12. Here, multiply 3 by every entry in the matrix, and then that gives us the matrix whose entries are 3, 6, and then multiply each of those by 2, and we get the same matrix, 6, 12. So we get this property, associative property of scalar multiplication. If you take a matrix A, multiply all of its entries by 1, what do you get? You get the matrix A right back. Because 1 is the identity element for multiplication for real numbers. It's also the identity element for multiplication, scalar multiplication. We're multiplying by matrix. The distributive property, I'll just kind of let you think about those, make up your own examples. We can take C and distribute it across the sum of 2 matrices. Or we can take a matrix and distribute it across the sum of 2 scalars, and it works out. There'll be some properties down a little bit lower that won't be as clear-cut. We might even use the calculator to create some examples to show us that, yeah, it really does work when we talk about matrix multiplication. But for matrix addition, scalar multiplication, they're pretty clear, I think pretty easy to see. Sometimes these end up being nice true-false questions on the test. True or false, if you have matrices that have the same order, so that matrix addition is actually well defined, is it true that A plus B is always equal to B plus A? Well, it is, because of the commutative property of matrix addition. The same for the rest of these. A matrix that we won't spend a whole lot of time with, the 0 matrix, if we needed an identity element for matrix addition, and we really won't so much. From time to time it may show up, but not so much in our cases. The identity element for matrix multiplication is going to be way more important for us. But in passing, we will just mention, if we have a matrix of a particular order, let's say 3 rows and 2 columns, and it has nothing but zeros in it, It has the property, when you add it to any other matrix with 3 rows and 2 columns, for example, then you get that matrix. It's like adding 0. You get what you started with. Or if you start with 0 and then add the matrix, you get the matrix. So I don't think we need to spend a whole lot of time verifying this. It is called the 0 matrix. It's the matrix of a particular order that consists of all zeros, but I don't think I need to consume a lot more time talking about it, because what's most important to us today is matrix multiplication. Matrix multiplication. It is a different animal from matrix addition. Matrix addition, you have a couple of matrices, you've got an entry in row 1, column 1, you add it to the entry in row 1, column 1, and the matrix that's going to be the sum is going to have the same order as the 2 matrices you're adding, and the entry in row 1, column 1 is the sum of these entries in row 1 and column 1 of the 2 matrices. Very simple. Matrix addition. Matrix multiplication, not so much. To boil it down, what we're going to do with matrix multiplication, to get a single entry in the product matrix, what's going to happen is we're going to take an entire column, wait, that's not a column, an entire row of entries in the matrix on the left, and multiply that number by number by an entire column of entries in the matrix on the right, and that will give us a single entry in the product matrix. It goes like this. We're going to multiply these 2 matrices together, A consisting of these entries, A sub ij, and B consisting of these entries, B sub ij, to form the product A times B. The orders have to mesh in a particular way. The matrix A can be an M by P, oops, sorry. P struck me as being odd there. An M by N matrix. So the matrix on the left can be whatever order we want it to be. The matrix on the right has to have the same number of rows as the matrix on the left has columns. So if this matrix that we're putting on the left to do the multiplication has N columns, the matrix we're going to multiply it by must have N rows, N by P. So they don't necessarily have to have the same order. M by N multiplied by N by P. And then when we multiply them together, we'll get a matrix that has M rows and P columns. An M by P matrix. So if we're wondering, is it legal? Is it allowed to multiply these 2 matrices together? Is it well defined, I guess is what I should say. These 2 numbers, well, I didn't do a good job with the arrow there. I'm going to try that again. These 2 numbers need to match. They have to be the same. If they are the same, then it's okay. The matrix multiplication will be well defined. And if we're wondering, well, what's going to be the order of the product, well, it's these 2. That's going to be the order of the product. The product will be an M by P matrix. M rows, P columns. So how do we get a single entry in the product matrix? Let's say a single entry in row I and column J, the entry C sub ij. In order to come up with that particular entry, we have to take an entire row of the matrix on the left. And specifically, it's row I of the matrix on the left. So if we have row 1, row 2, work our way down to row I, what does that look like? Well, A sub I1 A sub I2, A sub I3, and we work our way all the way over to the last entry. Now we know this matrix has n columns, so the last entry in that row is A sub I n. Okay, coming up with that C sub ij is going to involve all n of those entries in row I. We're going to take them one by one and multiply by the corresponding entries in column J of the matrix on the right. Where's column J? Well, there's column 1 right there, and then column 2. And if we work our way over, eventually we get to column J. B sub 1J is going to be the entry in row 1, column J. And then B sub 2J, row 2, column J. B sub 3J, right there. And then all the way down, this particular matrix has n rows. It's n by p matrix, n rows. So the entry in the bottom row, row n, and column J is denoted by B sub n J. So it's vital that the number of entries in this row be the same as the number of entries in this column. That's why the n's in the middle have to match up. N columns for the matrix on the left, n rows for the matrix on the right. And now we multiply. C sub ij, this one entry right here, we can get by taking A sub I1 and multiplying by B sub 1j. B sub 1j. Then we take A sub I2 and multiply by B sub 2j. Then we take A sub I3 and multiply by B sub 3j. And keep doing that all the way across the row and simultaneously all the way down the column until we get to the last one, A sub in multiplied by B sub nj, and then we add up all those products. We add them up, we get a single number, and we put that number right there. And that's the entry in row I, column J. So if we're forming a product and it has enough rows and enough columns to do this, we can multiply, say, for example, row 3 of the matrix on the left by column 5 of the matrix on the right, and that'll give us the single entry that's in row 3, column 5 of the product matrix. So if they have lots of rows, lots of columns, it may take a while to compute each individual entry. Now the calculator does do matrix multiplication if we have matrices full of numbers. So we'll use that to some extent. But what I'll do on the test is also throw in some variables to some matrices and ask you to multiply them out, just so I can be sure that you know how to do the computations, you understand how matrix multiplication is actually defined. Example 9, fairly simple, a simple matrix multiplication problem is when we take a row matrix and multiply it by a column matrix. The matrix on the left, if I want to multiply 2, 1, 3 by the matrix on the right, 4, 5, 2, we write down the order. 2, 1, 3 has 1 row and 3 columns. The 4, 5, 2, oriented differently, has 3 rows and 1 column. So we look at it and we ask ourselves, is the matrix multiplication well defined? Can we do this? We look at the 3's, and they are the same. So we're good. What will be the order of the product. And it's going to be one by one. It'll be a matrix with a single entry. It's going to be a one by one matrix. So I could write it as great big, but it's just going to be, I know that looks like the absolute value of x, doesn't it? It's not. It's one by one. That's the order of our matrix. And we get it just to see how the computations are done. Multiplying row 1 of the matrix on the left by column 1, the only column of the matrix on the right. So we multiply the 2 and the 4. This 2 by that 4. We multiply the 1 and the 5. We multiply the 3 and the 2. All the way across this row, all the way down this column. And we crunch those numbers, and we get a single number. What single number do we get? We get 19. 8 plus 5 is, what, 13? Plus 6 is 19. So we just get the number 19, and that is the final answer. And if they were only all that simple. Just multiply row by a column. But as the number of rows, number of columns increases, the number of arithmetic operations we have to do increases. So, nice one to start off with. Here the suggestion is that we do two different problems. Multiply A by B, and then flip it around, compare what we get if we try to multiply B by A. So one question could be, if it's defined in both cases, is A times B going to be the same as B times A? That is, for at least this example, is matrix multiplication commutative? If we reverse the order, we're going to get the same answer in both cases. So let's try AB first. AB equals the 2, 1, 3, 4, 0, 5. That has 3 rows, 2 columns. Going to multiply that by 4, negative 2, 5, 1, 3, 6. And that has 2 rows and 3 columns. Is this matrix multiplication well defined? Can we do it? We can do it because the 2's are the same. When we multiply them together, what will be the order of the product matrix? It's going to be 3 by 3. 3 by 3. Let's see if I can leave enough room to write all this out. I probably haven't made it big enough. Keep in mind we're multiplying rows of the matrix on the left by columns of the matrix on the right, and we get individual entries of the product matrix. So we can begin by multiplying the entries in row 1 by each column of the matrix on the right. So we're going to take the 2, 1 and multiply by the 4, 1. If you can do the mental math, or if you get the calculator to do it for you, it's not necessary to write down every little step, but probably in this first full-blown matrix multiplication example, I should be careful about writing each individual step, so you can go back and look at it later if you have any questions. So I'm going to multiply the 2 by the 4. I'm going to multiply the 1 by the 1. And we'll go ahead and summarize our results. The final answer is going to have what entry in row 1, column 1? Whatever 8 plus 1 is, I'm going to say 9. When you multiply row 1 of the matrix on the left by column 1 of the matrix on the right, we get 9. Then we multiply row 1 of the matrix on the left by column 2 of the matrix on the right. We're going to take the 2 multiplied by negative 2 and add that to whatever 1 times 3 is. We get the single entry in row 1, column 2 of the matrix on the right, and it's negative 4 plus 3. That's negative 1. We get negative 1. Then multiply row 1 of the matrix on the left by column 1 of the matrix on the right. Multiply the 2 by the 5. Multiply the 1 by the 6. There we go. 1 times 6. That's a rough 1 times 6 there. Let me try that again. 1 times 6. And 10 plus 6 equals 16. So think about it. We obtain the entries in row 1 of the product matrix by taking row 1 and multiplying by the successive columns of the matrix on the right. And that gives us the entries in row 1. What are we going to do next? I suppose a couple different things we could do next. But what I'd like to do is take the entries in row 2 and one by one multiply those by the columns in the matrix on the right, and that'll give us the entries in row 2 of the product matrix. We'll take the 3 and multiply by the 4 right there, and take this 4, sorry for the excessive number of 4s that I have in this example, 4 times 1. So 3 times 4 plus 4 times 1 equals whatever 12 plus 4 is. I'm thinking 16. Then for the entry in the middle of the matrix in row 2, column 2, we multiply row 2 by column 2. Multiply row 2 of the matrix on the left by column 2 of the matrix on the right. 3 times negative 2 plus 4 times 3. And we get whatever negative 6 plus 12 is. That's 6. And then for row 2, column 3, we multiply row 2 by column 3. 3 times 5 plus 4 times 6. And that's bigger. 15 plus 24 is 39, I think. Two down, 1 to go. We're going to take row, let's go green here, row 3 of the matrix on the left and multiply by the 3 columns of the matrix on the right, and we will get the entries in row 3 of the matrix that is the product. The 0 should help us here. 0 times 4 plus 5 times 1 equals 5. 0 times negative 2 plus 5 times 3 equals 15. And for the last one, 0 times 5 plus 5 times 6 equals 30. So that 0 entry means that we're basically just taking the 5 and multiplying it by the entries in row 2 of the matrix on the right. And that is the product matrix. That's what we get. Will we get the same answer if we flip it around and multiply B by A in that order? We will not. We can tell immediately that it won't be the same answer. It won't be equal to the matrix that we have. How can we be so sure? Yes, the order is different. Now the matrix multiplication is well defined. That's not always the case. If I multiply 3 by 2 by 2 by 5 and then try to reverse it, it's a 2 by 5 by 3 by 2, and the 5 and the 3 aren't equal. So we couldn't even do the multiplication. We can here because it's a 2 by 3 multiplied by 3 by 2. So we can do this because the 3's match up. But what is the order of the product matrix? not a 3 by 3. It's a 2 by 2. And when we defined what it means for two matrices to be equal, the first thing we said was they have to have the same order. They have to have the same order, and all pairs of corresponding entries have to be equal. But these don't have the same order. So there's no way that BA, see this is the matrix up here, AB, and this is the matrix BA, there's no way they can be equal because they don't even have the same order. Let's see if they have any matching numbers in there so they vaguely resemble each other. I'm thinking maybe not. So it's going to be a 2 by 2. And how do we get those entries? Well, we multiply rows of the matrix on the left by columns of the matrix on the right. So the 4, the negative 2, and the 5 get multiplied respectively by the 2, the 3, and the 0. And we add up those 3 products to get a single entry, row 1, column 1. So 4 gets multiplied by 2. Then negative 2 gets multiplied by 3. And then 5 gets multiplied by 0. We add all that up. 8 plus negative 6 is 2, plus 0 is 2. And we just get a 2 there. So 2 in row 1, column 1. Give myself a little more space. Why does it have to be so cramped? I don't know. Multiply row 1 of the matrix on the left by column 2 of the matrix on the right. And it's going to be 4 times 1 plus negative 2 times 4 plus 5 times 5. So 4 times 1 is 4. Negative 2 times 4 equals negative 8. 4 plus negative 8 equals negative 4. And negative 4 plus 25, 21. There we go. So 2 and a 21. And then the bottom row, we multiply the bottom row by each column. Take the 1, multiply by the 1. Take the 3, multiply by the 4. Take the 6 and multiply. What am I doing? What am I doing? I'm so sorry. Looking over, I could have put that in the other column, but I was looking at the wrong column. The 1, 3, and the 6 need to be multiplied by the 2, 3, and the 0. So let me try to get it right this time. Take the 1, multiply by the 2. Take the 3 and multiply by the 3. Take the 6, multiply by the 0. That's better. Multiply those together, and we get 2 plus 9 is 11. And then what I was doing a moment ago, multiply the 1 by the 1, multiply the 3 by the 4, and then multiply the 6 by the 5. We get 1 plus 12 plus 30, and that's 43. Not something that we should allow to consume a disproportionate quantity of our lives. The calculator will do this. If I go to second matrix and edit and make it a, let's see, matrix A is a 3 by 2, so make it a 3 by 2 and go with a 2 and a 1 and a 3 and a 4, 0 and 5. Second quit. Second matrix. Go in this time, I'll screw down to matrix B. Let's call this, or make this, edit this to be a 2 by 3 matrix. So that'll be 4. Four, negative 2, 5, 1, 3, 6. Second quit. Now, to multiply matrices, we don't have to go to the math menu like we do for RREF, reduced or echelon form, or the determinant, or any of those. We just go to the names menu, second matrix, matrix A, and then right up next to it, you can press the times button if you want to, but you don't have to. Just right next to it, second matrix, and select matrix B from the names menu, and it should multiply them when you press enter. There it is. That is the product AB. You can reverse it. Second matrix, select matrix B first. Second matrix A. If you multiply B by A, calculator figures out that needs to be a 2 by 2 matrix. And you see the entries there, 2, 21, 11, 43. You wouldn't really look at these and think that they came from the same two matrices, just reverse the order of the multiplication. So here's one example to indicate that matrix multiplication is not commutative, even if it's well defined in both directions. In this case, we don't even get the same order, so they don't commute. What if, what kind of matrix would you need? I guess two matrices. What kind of order would you need so that when you multiplied A by B and then flipped it around and multiplied B by A, there would even be a chance that they could be equal? Maybe a 3 by 3 by another 3 by 3. Then when you reverse it, it's still well defined and you would get a 3 by 3 as the answer. If you take a couple of square matrices, multiply them together, you get a matrix with the same order, so you reverse the order of the multiplication. I wonder if in that case you would have to get the same answer. Well, that question may have to wait a moment. I've got this application of matrix multiplication, back in the good old days when unleaded gasoline was $2.29? I don't know. When was that?
15 years ago.
Yeah, something like that. Let's say that the gas station has 4 pumps and 3 grades of gasoline. So you feel like there's going to be a 12-entry matrix. Pumps 1, 2, 3, and 4. What we see on a particular day, the following amounts of each grade of gasoline, these are measured in gallons, were purchased at these pumps. So 728.3 gallons of regular unleaded were purchased from pump 1. 179.8 gallons of unleaded plus pump 1. And then 214.5 gallons of premium unleaded were purchased at pump 1, and so forth and so on, all the way down that matrix. So we've got these two matrices, matrix A and matrix B. Matrix B is simply the price of the gas let's see, the regular unleaded, the price of the unleaded plus, and the price of the premium unleaded. If we multiply these matrices and form the product AB, first of all, is it okay? Can we multiply matrices of these two orders together? I think I want to copy and paste the whole problem. This one is 4 by 3. This one is 3 by 1. Is the matrix multiplication well defined? And the 3's match. So we say yes. It is okay to multiply these matrices together. If we do the matrix multiplication, we're going to use a calculator to do this because it's a real pain otherwise. What is the order of the product? Matrix on the left has 4 rows. The matrix on the right has 1 column. So the order of the product will be 4 by 1. Let's see what the calculator does with this. If I say matrix A, second matrix, edit matrix A, make that into a 4 by 3 matrix, and punch these entries in, goodness. Enter them by rows. Check my columns real quick before I type in matrix B. Seems okay. Second quit. Second matrix. Edit matrix B. Make that a 4 by 1. No, 3 by 1. Second quit. Okay, so just take use the names menu, second matrix A, and then right next to it, second matrix B, and the product matrix looks like this. Guess I should round each one to the nearest what? What do these numbers represent? Yeah, dollars and cents. 2641.74. 2641.74. And then 2782. Oh no, 2783.00. Looks like 1709.38. And 2253.40. So if the entries on the matrix on the left are amounts of gasoline purchased of the various grades at these pumps, and the entries in the matrix on the right are the price per gallon of each of the grades of gasoline, then the entries in the product matrix represent what? Well, what does each row of the matrix on the left represent? Matrix on the left, each row refers to what?
Gallons of gasoline.
Well, they all refer to gallons of gasoline, but if we break it down by row, row 1 is the number of gallons of gasoline purchased. Well, from pump 1. So each row there's a corresponding pump. Specifically. So row 2 is pump 2, row 3 is pump 3, and so on. Row 4 is pump 4. So the number $2,641.74 is the total amount of revenue generated from pump 1. Revenue from pump 1. And go down the column. Total amount of revenue generated from pump 2. Total amount of revenue generated from pump 3. I don't know what's wrong with pump 3. Maybe it's out of the way or something. And then the total amount of revenue generated from pump 4. So I didn't really give anybody time to ask when we're doing matrix multiplication. Would it be so much simpler if we just multiply this entry by this entry, and we get this entry as the product matrix? Could divide it like that, so that matrices of the same order, you can multiply matrices of different orders. You couldn't. This wouldn't be as useful. It's far more useful, the wide-ranging practical applications of matrix multiplication, if we multiply a row of the matrix on the right by a column of the matrix on the left to get an entry of the matrix that's the product. It just works so much better that way. And there we go. So I should have copied and pasted that one. Properties of matrix multiplication. Now we could generate examples for these. I've already got a matrix A and a matrix B in there. They're kind of rough looking. Maybe I should revise them to go with nicer numbers. If I had another section of pre-calculus this semester, I'd probably leave them there and use them for that other section. Don't have to type them in. But maybe what I can do is just, let's see, second matrix, make them a little nicer, in case we want to use them for examples. So I have a 4 by 3 and a 3 by 1. So let's just clean them up. Maybe I'll just keep the first digit, make that a 7. 1, 2, 6, 2, 3, 3, 1, and then a 4, and then I'm not rounding here, just keeping the first digit. Okay, so there's a 4 by 3 matrix with nicer looking numbers. 4 by 3, second quit, and then second matrix, just in case we need an example. Where is second matrix? Edit matrix B. And let's even go nicer here. I don't want all 2's. How about a 2 there, a 3 there, and a 4 there? Keep the digit in the 10th place. So do 3, 4. So there it is. There's an example of such a matrix. And I need one more. What should the other one be? Matrix C. So suppose I want to illustrate this A times B times C equals AB times C. And A is a 4 by 3 matrix. So A is a 4 by 3 matrix, and B is a 3 by 1 matrix. If I were to multiply those together and then be able to multiply that product by C, how many rows must C have?
1 by something?
1 by something. 1 by, I want to make it 1 by, we can pick any number for the number of columns, any whole numbers. Let's go with 2, just because we felt like it, or I felt like it. 1 by 2. So let's define another matrix. Second matrix, just keep punching the wrong button. Second matrix, edit this matrix C. Let's make it a 1 by 2 matrix, so we just need, it's a row matrix. A couple of entries of this row. How about a 3 and a -2? All right, so there we go. A times B times C. Second quit. If we multiply B times C, second matrix B, times second matrix C, we get that. So let me go with kind of a split screen here so I don't have to keep looking at it. So this 4 by 3 matrix, if I'm multiplying B by C, I get some matrix A by this. 6, -4, 9, -6, 12, -8. And let me just copy the A. I really forgot what it was. But second matrix, edit. What was the matrix A look like? It was something that looked like this. 7, 1, 2, 6, 2, 3, 3, 1, 2, and 4, 1, 2. Now I want to get the calculator to multiply these two matrices together. It's a 4 by 3 multiplied by 3 by 2. So it ought to give us a matrix of what order? 4 by 3, 3 by 2. Ought to be a 4 by 2. So how could I have the calculator do this? Basically, if I take second matrix A and I multiply by the answer. The answer is 6, -4, 9, -6, 12, -8. It'll give me this 4 by 2 matrix. The 4 rows and 2 columns. 75, -50, 90, -60, 51, -34, 57, -38. Okay. In the spirit of trying to show that matrix multiplication is associative, let's do this. Let's take A, which is a 4 by 3 matrix, and have the calculator multiply by B, which is a 3 by 1 matrix. Second matrix A, second matrix, again, second matrix B, and it gets this. Were you expecting it to be a 4 by 1 matrix? Hope so, that's what it is. We get, come on, we get 25, 30, 17, 19. Then we need to have the calculator, or we could do it ourselves. This shouldn't be all that bad. Multiply by matrix C. What was matrix C again? I guess I'm going to have to take a peek at it. 3, negative 2. It was just that. 1 by 2 matrix, which is 3, negative 2. Is it okay to multiply a 4 by 1 matrix by a 1 by 2 matrix? Is that allowed? Yes. And when we do, we're going to get a 4 by 2. So I think there is hope that we may get the same 4 by 2. If I take the answer that we got, there. If I take the answer that we got, second answer, and put that on the left, that's the matrix 25, 30, 17, 19, that 4 by 1 matrix. And multiply, should I press the times button? I feel like I could get by without pressing the times button. I don't want to mess this up though. What do you think? Should I press it or not press it?
Do it.
Okay. I'll press the times. I think you don't have to, but I'm going to press it nonetheless. Second matrix, from the names menu, I want matrix C. So this ought to multiply those together, and when it does, it gives us this. 75, negative 50. 90, negative 60. 51, negative 34. 57, negative 38. The process looks a lot different. If you compare these two matrices, this 4 by 3, this 3 by 2, to this 4 by 1 and this 1 by 2, a lot of different numbers there. Same final answer though. So if I take 3 matrices and multiply them in order from left to right, A times B times C, turns out not to matter whether we multiply the B times C and then multiply that on the left by A, or multiply A and B together first and then multiply that by C, as long as we don't change the order, just the grouping, we get the same answer. This means that matrix multiplication is an associative operation. Matrix multiplication is associative. Also, it's not going to be as crucial a property for us, so maybe I can leave you to generate your own examples. Matrix multiplication follows the distributive property. We can distribute matrix A across the sum of 2 matrices, whether A is on the left or on the right, but in both cases, notice, the order doesn't flip. Here, A is to the left of B, A is to the left of C, A is to the left of B, A is to the left of C. What's on the left and what's on the right doesn't change on each side of the equation. Likewise, in property 3 here, A is to the left of C, B is to the left of C, and when we're done, A is still to the left of C, B is still to the left of C. The order of the multiplication doesn't change in the distributive property. Scalar multiplication. Probably could throw in an example here, but it would mean having to do the multiplication. This one will not be a crucial property for us. Turns out it doesn't matter whether we multiply the matrices together first and then multiply every entry in the product by a scalar, or take that scalar, multiply every entry in one of the 2 matrices by that scalar, and then do the matrix multiplication. We'll get the same answer regardless. The key here, properties of matrix multiplication, is this. This one is true. This one is not. AB does not equal to BA, as a rule. Some cases, it's not even well defined in both directions. In other cases, it is well defined, but you don't get the same order. But even in the case where A and B are square matrices of the same order, and it's well defined in both cases, and you get a matrix of the same order in both cases, you might not get the same matrix in both cases. Here's the example. These are both 2 by 2 matrices. This is a 2 by 2, this is a 2 by 2. The 2's match, and so the product is a 2 by 2. If we multiply, we can just check an entry there. Multiply row 1 by column 1. We get 24 plus 56. 4 times 6 is 24, 7 times 8 is 56. So 24 plus 56 is 80. If we reverse the order of the matrices to do the multiplication, take the 6, 4, 8, 9, put it on the left. Take the 4, 7, 2, 1 and put it on the right. Even the first entry doesn't match. 6 times 4 is 24, 4 times 2 is 8, but 24 plus 8 is 32. And the other entries don't match up either. So even when you have 2 by 2 matrices, so matrix multiplication is divided both ways, and there's hope that they could be the same because they have the same order, they don't have to be the same. So matrix multiplication is not commutative. The order is important. When we reverse the order, there has to be something to tell us these matrices commute with each other. Otherwise, we cannot count on it giving us the same answer. Definition. We talked about the zero matrix a little bit ago. I didn't have too much to say about the zero matrix. Basically, the matrix of a particular order with nothing but zeros. You add it to another matrix of the same order, and you get what you started with. This one is going to be more important for us. With all the dots, maybe it's not entirely clear what we're talking about, so let me give some special cases. I sub 1, usually we don't have a whole lot to do with 1 by 1 matrices, but if we want the identity element for the set of 1 by 1 matrices, it's the matrix with just a 1 in it. You multiply this by another 1 by 1 matrix, and you get what you started with. Once they get bigger, we have to see what they look like. 1, 0, 0, 1. We put 1s from the upper left to the lower right, all along the main diagonal. We put 0s everywhere else. We'll check in just a moment. If I take this and multiply on the right by a matrix with 2 rows, or multiply on the left by a matrix with 2 columns, it's like multiplying by 1. We get the matrix that we multiplied this by. I sub 3. If I want a matrix I can multiply by a 3-row matrix and give me what I started with. 1, 0, 0, 0, 1, 0, 0, 0, 1. This is the identity element of multiplication for 3 by 3 matrices. And one more. Although they exist of all orders, it's got to be square. And if it has 1s on the main diagonal for a 4 by 4 matrix and 0s everywhere else, it's like multiplying by 1. I multiply this by a 4 by something matrix, and it's like I multiplied it by 1. It's the identity element for matrix multiplication. I usually don't take the time to put the little subscript there because it's usually clear what order I need. So I'll just call it I, the identity matrix, whatever order I happen to need. Matrix I, and give it the appropriate number of rows and columns. 1's on the main diagonal, 0's everywhere else. Fun fact about the identity matrix. It commutes with other square matrices of the same size. If I take a matrix 3, negative 6, 4, 0 and multiply by the identity matrix, it's like multiplying by 1. So that gives me 3, negative 6, 4, 0. Let me make sure that's believable. Kind of interesting, I think, to see just how that works. By multiplying this row by this column, 3 times 1 is 3, negative 6 times 0 is 0. So it just picks off the 3. And we put a 3 there. If I multiply by this column, 3 times 0 is 0, negative 6 times 1 is negative 6. It just gives me the negative 6. So in so doing, it just copies and pastes the top row there, and something similar happens for the 4, 0 down below. So if I take a 2 by 2 matrix and multiply by the identity, I get the same 2 by 2 matrix. If I reverse the order, you can check it. Take the identity matrix, multiply by 2 by 2 matrix. It's like multiplying by 1. You get the matrix you started with. So the identity matrix will commute with other matrices of the same order. And that showed up again. I'm not sure why I copied and pasted a little bit too many, maybe one too many times. one too many times, and it showed up again. We are approaching the fourth and final method for solving systems of 3 linear equations and 3 unknowns. Method 1, Gaussian elimination. We take the bottom one and get rid of what? Get rid of an x term and an x term and then a y term and use back substitution. That was Gaussian elimination. All the x's, y's, and z's. Method number 2, we took all the entries and we made a 3x4 augmented matrix. And either by hand with R sub 1s, R sub 2s, and R sub 3s, if you remember those, we put it into reduced row echelon form, or we had the calculator, put it into reduced row echelon form, and we solved it that way. Method number 3, Cramer's rule. Remember Cramer's rule with the determinants? Method number 4, using the inverse of a matrix. And we're almost to method number 4. I believe we've already seen this, or maybe we haven't. We can represent a system of linear equations by a single matrix. We can also represent a system of linear equations by a matrix equation. Matrix equation. Suppose we have the matrix A, this 3x4 matrix, 3x3 square matrix there, and let X, big X, be a matrix, a column matrix consisting of an x, y, and a z. Basically, it holds the variables for our system. And negative 4, 4, 2, this matrix is going to hold the numbers on the right-hand side. So consider this system down below. If we extract the key features, key information from this system, the coefficients go in this square matrix A, which is called the matrix of coefficients. So from the x we get the 1, from the negative 2y we get negative 2, from the z we get the 1, from the fact that there's no x term there we get a 0, from the y we get a 1, from the 2z we get a 2, from the 2x we get a 2, from the 3y we get a 3, from the negative 2z we get negative 2. So we extract the coefficients of each of those entries, and that makes a 3x3 matrix. Call that the matrix of coefficients. Well, this entire matrix is the matrix of coefficients. X, we'll call that the matrix of variables. And B, matrix of constants, where we get the numbers on the right-hand side. What I want to try to show is that the equation AX plus B is equivalent to this system. That is, if I write the equation big A times big X equals big B, I'm saying exactly the same thing as I would say if I said x minus 2y plus z equals negative 4, y plus 2z equals 4, 2x plus 3y minus 2z equals 2. Just doesn't take as long to say it if I say it with the matrix equation. So here goes. AX equals B. 1 times negative 2, 1, negative 2, I'm just listing the entries of the matrix. 1, negative 2, 1, 0, 1, 2, 2, 3, negative 2, x, y, z, multiplying by that matrix equals negative 4, 4, 2. That's the matrix equation. 3 by 3 matrix. Is it okay to multiply a 3 by 3 matrix by a 3 by 1 matrix? That's okay, because the 3's in the middle match. What will the order of the product matrix be if I do that? 3 by 1. So far, so good. That's what we're saying. Why does it mean the same thing as this? Well, let's go ahead and multiply the two matrices on the left. Since we can, let's do it. We're going to multiply rows of the matrix on the left by columns of the matrix on the right. And I'm going to get a great big 3 by 1 matrix on the left. So what I'll do is I'll say 1 times negative 2 times 1. All right, I'm not saying times. I'm so sorry for saying that. 1, negative 2, 1. I want to multiply by these 3 entries. What I'm multiplying is this. 1 times x, there. That's where the appropriate use of the word times. 1 times x is x. Negative 2 times y and 1 times z. Maybe I should be a little bit more deliberate than that. So 1 times x plus negative 2 times y plus 1 times z. The entries in the row on the left multiplied by the corresponding entries in the column on the right. Then I take the 0, the 1, and the 2 and multiply those by the x, the y, and the z. It's going to be 0 times x plus 1 times y plus 2 times z. I have to cross my z's, otherwise they'll look exactly like my 2's. And then the 2, 3, and the negative 2. 2 times x plus 3 times y plus negative 2 times z. Now on the right, just copy and paste the negative 4, 4, 2. I've got to simplify this a little bit. When we simplify, it looks like 3 entries, but it's really just a single entry. If you give me an x, a y, and a z, I can crunch the numbers and I'll give you a single number. It's x minus 2y plus z. That's the lone entry in row 1. And then y plus 2z. I deliberately kind of stagger them because that's the lone entry in row 2. And then 2x plus 3y minus 2z. That's the lone entry in row 3. So both these are 3 by 1 matrices. This is a 3 by 1 matrix, and this is a 3 by 1 matrix. When, under what conditions, are 2 matrices equal? Because the equation, matrix equation, declares that these 2 matrices are equal to each other. They have to have the same order, and they do, 3 by 1, 3 by 1. In addition to having the same order, what else has to be true? If I say this matrix on the left is equal to that matrix on the right, then it must be that what?
Each value on the left equals the one on the right.
Yes. So x minus 2y plus z must equal negative 4. And y plus 2z must equal 4. And 2x plus 3y minus 2z must equal 2. So, back up here. For these 3 matrices, when we say a times x equals b, what we're really saying is x minus 2y plus z equals negative 4, y plus 2z equals 4, and 2x plus 3y minus 2z equals 2. It's 2 really different looking ways of saying exactly the same thing. Now here's the thing. We want to set this up as a matrix equation and solve the matrix equation. So basically what we need to figure out is x. That's the matrix that holds the variables. If we can figure out what x is, we'll have it. That's the solution, the values of x, y, and z. So we're basically going to try to solve this matrix equation for x. That's what we'll do. Suppose we don't have a matrix equation. Suppose we have just a one variable linear equation. 3x equals 12. How do you solve that?
Divide by 3.
Was that 3 or 4 algebra classes ago? Divide both sides by 3. You say 3x divided by 3 equals 12 divided by 3. And what we usually do is just call the left-hand side x, right? Because we know the 3's are going to divide out. We call that x, and we get x equals 4. And then we got it. 4 is the solution of that equation. All right, suppose, well, we've got an issue. We'd like to do something kind of like that to solve our matrix equation, ax equals b, except with our matrix equation, we don't know how to divide. We can add matrices, we can subtract matrices, we can multiply by matrices. Whoa, wasn't that fun to do? But if we don't have a way to divide by a matrix, we haven't defined matrix division, and really, we're kind of not going to. There's really not a nice way to define matrix division. So let's back up to this one and see how we would go about solving this, and we can still do it, if we can't divide. Division is not allowed. You can only multiply.
Multiply by 1/3.
There you go. Multiply both sides by 1/3. We can say 1/3 times 3x equals 1/3 times 12. Now 1/3, why 1/3?
The inverse of 3.
It's the inverse of 3. Inverse for multiplication. It's the number that gets us back to the identity element. Because what we want here, when we multiply the 1/3 by 3, we want that to be 1. Basically, we've got the 3. We don't want the 3. We want a 1 instead. So we ask ourselves, what can we multiply 3 by to get 1 is the answer? 1/3. Now, another way to write the 1/3 would be this. How do you feel about 3 to the negative 1? Is that okay? We're good with our negative exponent rules. Yeah, that means 1/3. So we can multiply 3 to the negative 1 by 3, and that gives us 1. So 1 times x equals, 3 to the negative 1 times 12. Can we just go on the belief that that's 4? I don't think we want to twist our minds around that. That's a third of 12. That's 4. And 1 times x equals little x, and that's 4. Something similar to that we want to do with the matrices. Here's what we want to do. We need a matrix. We can't divide by A. So we need a matrix that we can multiply by A, and it'll give us ultimately x down here, but A, we're going to call it A inverse if it exists. We want to multiply that by A so that it gives us the identity matrix. If A is a 3 by 3 matrix, we want to multiply that by some other matrix that will give us the 3 by 3 identity matrix. So we're thinking this is going to be a 3 by 3 matrix, so we'll get I as the answer. I'm not doing Roman numerals here. I is the 3 by 3 or whatever order. Identity matrix, X is the matrix with nothing but variables. We'd need to multiply both sides by that mysterious matrix. But if we did, if I take this 3 by 3 matrix that kind of unlocks the key to this system, and I multiply by those constants on the right-hand side, we can multiply a 3 by 3 by a 3 by 1, and then we'll get a 3 by 1 matrix, and it will have the solutions to the system. Now, once we get this matrix, A inverse, we're going to call it, if it exists, it's pretty straightforward. A calculator just multiply it by B. The process of coming up with it takes a lot of computations. So we want to see how we would go about doing that. But first, just if I take this matrix and multiply by this matrix, am I going to get the identity matrix? Well, in 5 minutes, I think we can show that these two matrices, in fact, are inverses of each other. Maybe I'm overly ambitious, but I think we can do it. I just want to show that we can take the 3 by 3 matrix that you see on the left and multiply by the 3 by 3 matrix on the right and get the identity matrix as the answer. So if I had a system with 1, 2, 0, 2, 9, 1, 0, 4, 1 as the matrix coefficients, I could solve it pretty easily by multiplying both sides by this matrix on the left. Well, what happens? 5, negative 2, 2, negative 2, 1, negative 1, 8, negative 4, 5. it will be an inverse for this matrix on the right if I multiply these together and get the identity matrix as the answer. So only 9 entries. 9 entries in, what, 4 minutes? I better go at a pretty good clip here. All right. 5 times 1 is 5. Negative 2 times 2 is negative 4. 5 plus negative 4 equals 1. And 2 times 0 is 0. So 1 plus 0 is 1. So we get the 1 there. 5 times 2 is 10. Negative 2 times 9 is negative 18. And 2 times 4 equals 8. So it's going to be 10 plus negative 18 plus 8. Does that sound like 0? I hope so. 5 times 0 is 0. So it's going to be negative 2 times 1, that's negative 2. 2 times 1, that's positive 2. So it's 0 plus negative 2 plus positive 2. And that's 0. 1 down, 2 to go. Multiply row 2 by each. Of course, your calculator will do this. If you punch the 3 by 3 matrices in, your calculator will do this. Negative 2 times 1 equals negative 2. 1 times 2 equals 2. And negative 1 times 0 equals 0. So it's going to be what? Negative 2 plus 2 plus 0. That's 0. We need 1 in the middle. Negative 2 times 2 equals negative 4. 1 times 9 equals 9. And negative 1 times 4 equals positive 4. No, negative 4. So what's it going to be? Negative 4 plus 9 plus negative 4. Is that 1? Mm-hmm. Yes, more than halfway home. Negative 2 times 0 is 0. 1 times 1 equals 1. And negative 1 times 1 equals negative 1. So I think that's easy. 0. What is it? Here it is. 0 plus 1 plus negative 1. That's 0. 2 down, 1 to go. 8 times 0 is, no, sorry, 8 times 1. 8 times 1 is 8. Negative 4 times 2 equals negative 8. 5 times 0 is 0. So it's 8 plus negative 8 plus 0. That's 0. 8 times 2 equals 16. Negative 4 times 9 equals negative 36. And 5 times 4 equals 20. What is 16? 16 plus negative 36 plus 20. Is that 0? Yeah. Need 1 in the lower right-hand corner. 0 plus negative 4 plus 5. That's 1. Now, 3 and 1/3 kind of look alike. You can see they have the special relationship to each other. If you multiply them together, they're multiplicative inverses, you get 1. If you saw this matrix and this matrix, I don't know, walking down the street somewhere, would it occur to you they had this special relationship that when you multiply them together, you get the identity matrix? Well, they do, and we'll use this at the beginning of class next time.